It's the solving a really complex problem by piecing lots of things together. Experiments, thoughts, ideas, theories, other people's ideas, and then eventually sort of beginning to feel your way and suddenly say, yeah, that's the answer. And it's just like this amazing feeling that you've solved this hugely complex problem, which might even have some applications in real life. The research my group does is essentially working out what the molecular structure of tissues are. Tissues like our skin, bone, tendon. And the reason we do that is that obviously in degenerative diseases, things go wrong with that, often drastically. And that causes the cells in those tissues to essentially misbehave. And so to try and do something about that, we first of all need to know what's going wrong with the tissue, how the tissue structure changes, and then we can start to piece together why the cells react the way they do, and then we can start to counteract that effect. A project that we've been working on for around 20 years now is hardening of the arteries, vascular calcification. And through sheer serendipity, we discovered the mechanism of how that happens. And as soon as we'd worked out how it happened, we were able to devise ways to stop it. So we've already got a patient trial going in Addenbrooke's. Now we're looking for, if you like, the next generation solution to that problem. And so now we're delving even deeper. And for me, this is a real new thing. We're delving into how the cell behaves and how the cell causes that calcification. A big new project for my group is cancer. So in cancer, we all know cancer cells move, metastasis. And that's the damaging part of cancer, is when those cells go on the move. To move, they've got to move through a tissue. So they have to change the structure of that tissue. So we're looking at how cells do that, how it is they get through, and what we can do to block it. The way we study the molecular structure of tissues is through nuclear magnetic resonance spectroscopy. And to do that on a real tissue, you first of all got to put carbon-13 and nitrogen-15 isotopes into a real tissue. And so we developed a way of doing that in animals and in vitro tissues. And so that's now, it's kind of opened up quite a big area for studying tissues at the atomic scale with NMR spectroscopy that other people are now using. In terms of, say, real life applications, as I said, there's a patient trial going on in Addenbrooke's around hardening of the arteries using a minocycline as a part 2 inhibitor. And that's trials happening in stroke patients right now. In terms of the cancer work, we've set up a company to follow that. We do have some significant leads to stop cancer cells moving, doing something to the extracellular matrix, doing something to the tissue around the tumour to prevent the cells moving. And we're now talking about doing that, taking that to the next stage towards the clinical. What happens when you overstretch a tissue? We know it breaks, cells repair it. But what happens if you do it again? The cells don't just repair it, they strengthen. So there's some encoding into your tissue about the damage that's happened, not just the damage that's immediately there, but the history of the damage, so that cells know whether to just repair or do a better job than that. So we've started looking at that. We started looking at what are the chemical markers in a tissue that tell a cell this bit's been damaged before, we need to repair it much more heavily. And we're using NMR to do that. And that's a tremendous challenge, because now we're doing NMR spectroscopy, not just on a piece of tissue, but on a piece of tissue that's held stretched or is even being moved in real time. So that's a real technical challenge. It's also an immense challenge because we've discovered mechanochemistry going on in that tissue when you stretch it. And that chemistry is incredibly diverse. And so piecing that together is going to be a large mountain, but I think it's going to be one that's going to be well worth climbing. You have to aim there and expect to get to there, and occasionally you get there, and it's kind of nice. My group's very diverse in every respect, and there are people from literally all around the world there. I think one of the best group activities is we celebrate a lot. So papers, first year reports going in, first talk, second talk, and cake and coffee are definitely the order of the day for those sorts of things.